All right, hello everybody. Today what we're going to cover is oxidation of alkenes and oxidation of alcohols. So it's a very important lesson, and so I'll need you to stay focused. Hopefully you have printed out either a copy of this or you have a notebook ready to take notes in. And then remember, we will have class on Wednesday to discuss and do practice questions on this topic along with everything that we've covered so far. We want to, hopefully, if we can, be done with chapter 18 by the end of next week. So we should be done with organic part 2 by next week. And so let's go ahead and get started. As usual, I will ask questions throughout, and you will need to answer those questions. The Ed Puzzle lessons are for a grade, a comprehension grade, and to make sure that you are going through and trying to understand the topics before we meet together. I understand that organic chemistry is not the easiest topic to learn remotely or virtually, so I am trying my best to come up with ways for you to understand as we go along and not to take away from class time, because we used to have 5 hours and now we have less time together. All right, so let's go ahead and get started. So what you'll notice is chapter 14 part 8 and chapter 17 part, and this is actually part 2 because I'd actually combined the first 2 parts together. So for you, this is part 2 of chapter 17 and the last part of chapter 14. So you can find oxidation of alkenes in chapter 14, and you'll find oxidation of alcohols in chapter 17 in your textbook. I know some of you are using your textbooks, and that is really helping you out. So these are the places to refer back to as you are going to be working on your lesson objective summaries shortly. All right, so first of all, just a reminder of what is basic oxidation. Before we learned about charges and electron transfer, oxidation is simply the gain of oxygen. So when a molecule gets more oxygen, that's the organic chemistry standpoint of what oxidation is, or the removal of hydrogen. So if I remove hydrogen or if I add oxygen, both of those factors are considered to be oxidation. So let's go ahead and take a look at the learning objectives. And so describe the chemistry of alkenes as exemplified by the following reactions of ethene. Now, ethene is an example molecule. We will see this for many other molecules. It says oxidation by cold, dilute, acidified, and you should go ahead and memorize the conditions. Manganate ions to form the diol, and oxidation by hot, concentrated acidified manganate to rupture the carbon-carbon double bond to determine the position of alkene linkages in large molecules. And then with oxidation of alcohols, we're going to learn how to oxidize alcohols and what conditions we're looking for in order to do that. And then this last objective right here, we are going to save for another lesson, mild oxidation to favor the aldehyde instead of a carboxylic acid. So this one we are going to save for the future, but today we are going to really focus on those oxidation reactions. What do they look like? Predicting the products. A lot of your Cambridge questions for paper 2 are going to circulate around in the organic part 2 section, being able to look at a reagent or a reactant and see what it does with an organic compound. So without further ado, let's go ahead and get started with bell work. So as usual, I'm going to give you a little bit of time to work out the bell work and answer the question yourself, and then afterwards I will go ahead and solve it and we'll see if you got it right. All right, let's see if you got it right. So the first thing that I like to do is I like to rewrite out the molecule where I expand the ester bond. Whenever I see CO2C, that means that I definitely have an ester, and the single bond oxygen will be pointing in the direction that the oxygens are placed around that carbon. So this is going to be CH3, C, double bond, oxygen, single bond, oxygen, CH2, CH, CH3, CH2, CH3. And so what do we have to do? If we want to find out how to make this ester, we have to think back to where do we break this bond. And we learned even when we named it, where did we break the bond? And the bond breaks in between the carbon with the two oxygens. And so remember that this is the carboxylic acid side, the side with the double bond oxygen, and the other side is the alcohol side. And so now all I have to do in order to formulate my answer is take a look for the carboxylic acid and for the alcohol that matches. So for the carboxylic acid, it is 2 carbons long with the carboxylic acid. And so A and B are out, and it can either only be C or D. And so then we have to look at the other side. The alcohol is attached to a carbon that on the next carbon there's a methyl group. So 2, carbon 1, carbon 2. All right, let's see. Carbon 1, carbon 2, methyl group. This one is carbon 1, carbon 2, carbon 3, methyl group. Remember, they swapped the molecule around. They put the alcohol on the opposite side, so you do have to count from the alcohol. So although I counted left to right in mine, in the multiple choice question, I had to count from right to left because it's where the alcohol is at that determines the placement of carbon 1 and carbon 2. So if it's 1, 2 here from the alcohol, then here it's 1, 2 from the alcohol, and the answer is C for the bell work. So if you got that, whoop, whoop, pat yourself on the back. And let's go ahead and get started with the lesson. So, oxidation. Starting with alkenes. So again, there's going to be 2 major concepts in here. What do we do with alkenes? And then what do we do with alcohols? And so alkenes are oxidized by adding KMNO4. And so if it's acidified KMNO4 and it's cold and it's in dilute acid, what's going to happen is just the double bond's going to break. When that double bond breaks, you have this as a result. And so these carbons currently only have 3 bonds, and they need to have 4. So the KMNO4, because you've got so much oxygen there, it's a provider. You can think of it as a provider of oxygen. So if I see a ton of oxygens on a molecule, I think of it as a provider of oxygen. So therefore, it's probably going to be able to be used for oxidation. And so what I add is where this used to be just nothing, because it was a double bond there, I add OH. And here I add another OH. And so I add an OH to each side of the carbons that had the double bond. So that would be the carbon here and the carbon there. And I end up with what's called a diol, which means 2 alcohols. So add 2 OHs if you see cold KMNO4 and you see an alkene. That's the recipe. Let's take a look at some practice examples with this. And I am going to use skeletal format. However, you are responsible for understanding all formats, skeletal, displayed, and structural. So let's take a look at a couple of examples. So above and below the arrow, you can write your reactions and conditions, and then your organic molecule on the left. And so what happens, KMNO4, cold, dilute H+, is you do break just the double bond, and so your product would be in order 1, 2, 3, 4, 5 carbons, and then where the double bond used to be, you mark those specific carbons, and you add OHs to both sides. That's it. Well, what if I had multiple double bonds? If I had 2 alkenes, or 3 alkenes, or 7 alkenes, well, what would I do? Don't think too hard. 1, 2, 3, 4. Oh my God, Miss Lee, what are you doing? Okay, so let's say I had KMNO4, cold, H+, dilute. How many alcohols would be added? Let's see if you got it right. How many alcohols would be added to this molecule? So I'm going to mark each of the carbons that had a double bond. Right? All of them had a double bond. So I would add an OH to each side of the carbon that has a double bond. So an OH pretty much to every carbon. So that would be, whoa, 8 alcohols added. Whoa. But the idea is that every time I see an alkene and I see cold KMNO4, I am adding an alcohol to both sides of where the double bond used to be and breaking just the pi bond, which is the second bond that connects the 2 carbons together. And so this is actually the easy type of molecule. Well, let's look at one more just for good measure. Same reagent. So it's a ring. Oh no, Miss Fleet. We saw a ring opening on Friday. Well, this ring doesn't open because in order for the ring to open, both bonds would need to be broken. So we are only removing this bond. So my answer would be OH, OH, and that's all it is. It's terribly drawn, but I think you got the idea. All right, so cold KMNO4, done. So how do we oxidize hot KMNO4 in an alkene? What is the difference? And so hopefully it should make sense that at a high temperature, not only do you break the single bond of an alkene, you actually have enough energy to break the double bond of an alkene, and you form 2 products as a result. And so the idea that happens is if you have, for example, this alkene, right? And you have hot KMNO4, the whole entire bond breaks. And it's kind of like if you've ever had one of those chicken wishbones and 2 people get the 2 halves of it, you end up with the 2 halves of the molecule. And so instead of the carbon with the double bond connecting to a carbon, the general idea is that you add oxygens in the place. So that'll get oxidized in that location. And so here's what we're going to be looking at. If I had a double bond carbon with 2 hydrogens attached to it, that is going to become CO2. I'm going to add, instead of those 2 hydrogens, I'm going to have 2 oxygens in those 2 hydrogens place. If I had an CH3, so I had a hydrogen connected to one carbon and a CH3 connected on the other side to that carbon, I end up with adding an oxygen here, right? And adding an oxygen here, but I can't add an oxygen where there's a carbon. So I end up with a carboxylic acid as a result. And then finally, if on one of the sides that gets broken, I have this situation, I add my oxygen. I cannot add an oxygen to a carbon. I cannot add an oxygen to a carbon, so it remains as it is, which is not an aldehyde. It is actually a ketone. So, seems like a lot, and I know it is. Let's take a look at a few more examples. What does this look like? And so, cleave this bond, break the whole thing apart, and you look at each side individually. H3C, C, H is the left side. Always add an oxygen. And then if there's a hydrogen, add an oxygen. And so that's a carboxylic acid on the left side. Done. On the right side, I told you if you saw 2 hydrogens, just know that it becomes CO2. But how so? I know that I add the oxygen where the double bond was, but the other thing that we usually do is we add an oxygen to each hydrogen. So why does this become carbon dioxide? Although you don't really need to know for this class, I am just going to say that the reason why is because this molecule is actually extremely unstable, the one that forms by oxidizing the hydrogen twice. And so what happens is water leaves, and you end up with OCO, and then you complete the octet rule, and it becomes carbon dioxide. And it's a simple view of how that happens. For the second one, it's symmetrical, if you'll notice. And so I end up with H3C, C double bond going to, instead of carbon, remember that that is being broken apart, and instead of that carbon, we are now adding an oxygen to each side. And where I see a hydrogen, I add an oxygen. So this is a carboxylic acid on the left side. And there's a hydrogen on the right side, so I add an oxygen. So it's a carboxylic acid on the right side as well. And that's what you should see here. And then for the final one, H3C, C, break, CH3. And on the other side, CH, CH3. I have an oxygen here. I have an oxygen here. So then there's no hydrogens that I can add to the left side, so it's stuck as a ketone. And on the other side, I can add a hydrogen here, so it's a carboxylic acid. So ketone and a carboxylic acid. So an easy procedure is to add oxygens where you see the hydrogen on the carbon that has the double bond oxygen after adding the oxygens. Let's take a look at a few more examples. Let's look at this. So hot, KMNO4, everything else is the same, dilute and acid. You can either specify the acid or just write H+. And so now what we have to do is we actually have to break the molecule up. So just break it right there. And so you write it as two separate products. You retain the double bonds, except now the double bonds are not going to carbons anymore because the carbon was ripped away. It's now going to oxygens. And so then I analyze the carbons that have the double bond oxygen. This carbon has 1, 2, 3 bonds, which means the other bond must be a hydrogen. And I told you whenever you see a hydrogen in an oxidation, it's actually going to add an oxygen, so this would be a carboxylic acid. And this other carbon already has 4 bonds, which means that there's no hydrogens on that carbon, so this ketone would retain as is, and that would be your product. Let's take a look at one more. One that I think is a little bit spicy. That's a ring. It's a cyclohexene. And so how would we do this? What would we do if we were to react this with KMNO4 and hot dilute H2SO4? So when we break this bond, we basically open the ring. And so instead of writing the 6 carbons in a ring, you write them out in a line. So my suggestion is to label the carbons 1, 2, 3, 4, 5, 6, and now to write them out in a line. 1, 2, 3, 4, 5, and 6. And then remember where the double bonds were at. They were on carbon 1, so have the double bond reaching out on carbon 1, and have the double bond reaching out on carbon 6. And now do the same thing that you would otherwise. You add the oxygen, and then analyze the carbon. The carbon on carbon 1, carbon 1, has 3 bonds, which means it has a hydrogen, which means I need to add oxygen. It's a carboxylic acid. And on carbon 6, it has 3 bonds, so that means there's a hydrogen, and that means I need to add an oxygen again, and it's a carboxylic acid, so it's a dicarboxylic acid. And that would be my answer when I break up the ring. So the easiest way to break up the ring is to count the amount of carbons in the ring and then to line them in a line, zigzag line, the same way we usually do skeletal, and then to just add the double bonds at the appropriate carbons. Okay, so this question I'm going to come back to. We can't answer it quite yet because this molecule not only has an alkene in it, it also has an alcohol. So we have to discuss how oxidation of alcohols happen before we can answer this question. So let's get to it. Reactions of alcohols, oxidation and reduction. So there's a simple way to memorize this. And I'm also going to show you a little bit of the why behind the what. Again, there really are no mechanisms here for you to know, which for some of I'm a mechanism girl, so I prefer knowing the mechanisms, but there really is no easy mechanism here to memorize. So it's basically just knowing the recipe. But I will show you reasoning that'll hopefully make it make some sense. And so the idea is that primary alcohols will become aldehydes. But aldehydes will never stay aldehydes. They will always turn into carboxylic acids. Secondary alcohols will become ketones, which cannot be oxidized anymore. And tertiary alcohols can actually never be oxidized. And so we're going to go a little bit over why that is. Something you have to know is the reagents and conditions. The reagents are alcohol, K2Cr2O7, and dilute H2SO4, but you could either use Cr2O7 and any metal ion. It is the dichromate that is the provider of the oxygens you need to do the oxidation, but you could actually also use MnO4- and you can also oxidize alcohols that way. What I accidentally left out in this PowerPoint is the condition. The condition is also to heat under reflux. So a lot of times whenever we're working with organic molecules, we need to heat under reflux. And so let's take a look at this a little bit closer. And so if I have a primary alcohol, the idea is that I remove two hydrogens. Remember that oxidation is either adding of oxygen or removal of hydrogen. So I remove two hydrogens, one on the oxygen and one on the same carbon, but the hydrogen next door. And so I end up with this. Well, right now, this does not satisfy the octet rule. So in order for it to satisfy the octet rule, it would have to be a double bond with the oxygen, which makes it an aldehyde. But whenever I have an aldehyde, unless I do specific conditions, which we have not looked at yet, it will actually turn right into a carboxylic acid very shortly afterwards. So what you need to notice is that when you see a carbon with a single hydrogen next to it and you are oxidizing by oxygenating it, by adding an oxygen, and so it becomes a carboxylic acid. Secondary alcohol, if we analyze the structure, I do the same thing. I take two hydrogens away, one from the, and I have to take both of them away or else I can't form the bond. I take away the hydrogen from the oxygen and the hydrogen from the carbon, and where here I would have R, C, R, single bond oxygen. When I take those two hydrogens away, in order to satisfy the octet rule, I do have to add that double bond, and so that makes a ketone, and a ketone cannot be further oxidized because I can't just throw in an oxygen. So no reaction will happen if you are asked to oxidize a ketone. And then finally, for the tertiary alcohol, so in order to oxidize it, I need to take a hydrogen away from here, because the whole idea is I'm supposed to end up with this. Well then, I can't take away a hydrogen from the carbon because there are no hydrogens on the carbon. So I am stuck, if I try to put that double bond there, I'm stuck with a carbon with 5 bonds, which is a big no-no. So tertiary alcohols do not get oxidized, partially for that reason. So, what are the conditions? As you saw, you can use dichromate and dilute H2SO4, and solution must be warmed, which the actual condition is heat under reflux, is the term that is used by Cambridge. K2Cr2O7 itself, because dichromate is a transition metal, and I don't know if you remember, I told you earlier in the year, transition metals are often colored. So the K2Cr2O7 is actually, and it's the dichromate itself, is orange. It's comes orange, that's its natural color. Alcohol is colorless, see-through, and dilute sulfuric acid is also colorless as well. So we have colorless alcohol, we have orange Cr2O7, and we have colorless H2SO4. So when we mix all of that together, it looks like that. And so the idea is that when you are oxidizing the molecule, alcohols, aldehydes, ketones, and carboxylic acids, they're all colorless, actually. Your organic molecules are colorless. So it's actually the ionic compound that's being reduced, the K2Cr2O7, it's being reduced, that is what's showing the color. And so the color will turn from the orange if it's been oxidized to green, to dark green. And you do need to know that proof of oxidation with CR207 is a change of orange to green. You should write that down in your notes because you'll get a lot of questions, especially in the paper 1, that ask about color. And so I do want to point out that for MnO4, there's actually a color change there. For MnO4, if you were to use that instead, permanganate starts out as a purple color, and it changes to colorless when oxidized. So go ahead and write that down because that is the color changes that you need to be aware of. And so let's take a look at what these Cambridge questions could look like. How many of the following compounds, and actually, let's go back. Let's go do this other Cambridge question we were supposed to do. We have enough information now. So what is produced when this compound P, which is up here, is treated with an excess of hot, concentrated, acidified KMNO4? And so if it's concentrated, it's definitely going to do what dilute does, which is to break the double bond, but it also will oxidize the alcohol. So what I'm going to notice is that I need to break this double bond. And so I'm just going to write an answer for the left and an answer for the right, and then look for those 2 answers. So CH3, CH2, I'm going to expand the carbon that has the double bond. So I'm going to write the hydrogen on the side. I always like to expand the molecule or write displayed right around where the reaction is occurring, at the part which it's occurring, so I can see what's going on there. I can leave everything else condensed. So when it breaks up into 2, I have to add the oxygen where the double bond carbon used to be. And if I see a hydrogen by itself next to that carbon, then I have to add the other oxygen. So this will be a 3-carbon long carboxylic acid for the left side. So that's the left side. All right, well, what about the right side? So I'm going to write out double bond C. I'm going to expand that. So that's an H, and then CH2, CH2. Oof, I'm going to think about what my product is here. So then I add the oxygen here, and that's a hydrogen, so I add an oxygen. And then on this side, this is a primary alcohol. So a primary alcohol is going to turn into an aldehyde, but it's not going to stay an aldehyde. It is going to turn into a carboxylic acid. So this would be a carboxylic acid as well, because alcohols, remember, if they're primary, will always turn into carboxylic acids. They won't remain aldehydes. So my answer would be, I need a carboxylic acid with 3 carbons, and I need a dicarboxylic acid with 3 carbons. And so that answer is D. Pat yourself on the back if you've got it right. All right, let's try this one. How many of the following compounds produce a carboxylic acid when heated under reflux with hot acidified K2Cr2O7? Okay. Do aldehydes become carboxylic acids? Yes. If we were to write it out, it would be CH2COH. And remember, whenever I see a hydrogen by itself next to a carbon, I'm going to add that oxygen there. So that is a carboxylic acid. So yes. So check mark. The second one, CH3. What is that? CH3C. Is that an ether or is that a ketone? Well, in order to fulfill the octet rule, it has to be a ketone. Because if it was an ester, it would be this. So notice the key difference. An ester looks like CH3OCH3, whereas a ketone is CH3COCH3. So if I see a C with an O right next to it, where I don't there, I do have a ketone. So this is a ketone. Ketones can't be oxidized any farther because I can't add oxygens onto this carbon anywhere. So no. The next one is a primary alcohol. So if you remember, primary alcohol becomes aldehyde, aldehyde becomes carboxylic acid, then we know that this one is correct. And so then the last one is a secondary alcohol. So a secondary alcohol, if we just write it out, CH3, CHOH, CH3, remove the hydrogen for the oxidation for first step. You end up with a ketone. Ketones can't be oxidized any farther, so you will not make a carboxylic acid. That alcohol has to be on the end to make a carboxylic acid. So therefore our answer here would be 2. And so this is the final question for today's lesson. Sorbitol is almost the final question. I think I want to cover one more. Sorbitol is an artificial sweetener used to sweeten chocolate, which is suitable for diabetics. And then they give you, this is called the Fischer projection of the molecule. And so sugars generally, when they're in water, they form ring-like structures. But this is that ring broken apart. It's called a Fischer projection. Usually it's shown with the bond angles, but here it's in a simplified format. So let's take a look at if we were to oxidize this molecule, what functional groups we would get. And it says under suitable conditions. So which can we get? Well, if I notice what type of alcohol I have, that will tell me my answer. This is a primary alcohol. Primary alcohols become aldehydes, which then become carboxylic acids. Because you take away, you add the double bond oxygen, and then you add an oxygen there. Secondary alcohols, which you see right there, will give me a ketone. So secondary alcohols will give me a ketone. Oh, so I produce aldehydes, carboxylic acids, and ketones, and that would be the answer. So if you got that, you got it right. And then we're going to do one more question. I'm going to skip this because we haven't discussed yet the conditions to keep an aldehyde. We will, but we have not. But let's take a look at what reagents and conditions would be used to oxidize propene-1-ol to propanoic acid. This will be your final question for the day. So you could have either wrote K2Cr2O7 with dilute H2SO4, heat under reflux, or you could have written KMNO4, and it doesn't have to be potassium once again. It could be just Cr2O7 minus 2, MNO4 minus. The metal ion does not matter. It is a spectator. It is the transition metal with the many oxygens that is giving the oxygens to your organic molecule. So then the rest of the conditions here would be dilute H2SO4, or you could even have just said H+, and heat under reflux. All right, that's it for today. Hopefully you have started to absorb this topic. Make sure to rewatch the video if you need to, and I will see you in class soon. Have a great day.